Hello, everyone, and welcome to our second vibration control webinar. This is a topic of vibration control, and it's on sign and shock testing this time. My name is Bill Flynn. I'm application engineer for Siemens out here in the Southern California office, and I'm joined today with my colleague, Charles Rice, and I'll let Charles introduce himself.
As Bill said, my name is Charles Rice. I'm also an application engineer for Siemens Simcenter Test Lab products, and I'm also stationed on the West Coast.
Okay, great. And let's go to the next slide here. Move things out of the way and position correctly. As I said, our agenda for today is sign vibration control. We'll also go into shock control testing and mention the classical and SRS, shock response spectrum types of shocks. Start off here with sign vibration control. This is positioning different types of environmental closed loop control based on frequency range. And typically, these are all rules of thumb, let's say. We talked about random control earlier, and that's in this kind of frequency range typically. Now, typically, sign control is in this kind of frequency range from the like about 4 hertz, 2 hertz, up to about 100, 110 hertz, something like that. The others are positioned here. Time waveform is a little bit lower in frequency, random in this frequency range, and then shock in this kind of frequency range. And these are all typical values, of course. So regarding vibration control, sign control, and the different scenarios where it'd be most applicable, let's say this is where the dominant type of signal is more sinusoidal in content. So let's say helicopters, rotating machinery type equipment, and the components that are associated with those structures, that's where you might consider sign vibration control. In looking at the SN curve and how the fatigue and damage is related to this application sign control, the amplitudes are a bit higher. Again, where the dominant frequencies are sinusoidal in nature, that's where you would apply this, and it's higher in amplitude and more in the higher elastic stress range and even maybe in the plastic region as far as the amplitude and the number of cycles go. Higher amplitudes, medium number of cycles. This would be typically modes, but we're going to focus on the sign sweep. And so you'll have some sinusoidal content and it'll be a sign sweep, and this can generate the fundamental sign frequency, but also the multiple harmonics of that, and you'll get responses sometimes. If there's some harmonics in the responses, you can get those, and that's going to be part of the signal that is measured. The sweeps cover all frequencies, but there's the sign dwell application is more for durability, where you dwell at particular frequencies. And then there's the sign on random, where you have the combined modes application. Sometimes there's some background present in operational conditions, but in this case, we're going to consider and make sure these apply the sinusoids sweep to generate higher level responses, well above some random background noise that's in the operational conditions. Another application here, but you had
I had
a
a quick question.
Charles?
Yeah, just about the dwells for the durability. Would they normally dwell at the natural frequencies of the structure, or maybe kind of a frequency related to an operating speed?
Well, it's typically at an operating speed. So like helicopters is a really good application, and they try to characterize the rotational frequencies, and they would identify those ahead of time. And then according to what we use typically for these applications for military standards, the MIL standard 810, they tell you to do these dwells at the operational frequencies, but you have to know what those are, and then they give you some guidelines on what kind of amplitudes and how to apply those as far as duration, some of the test setup parameters. So that's how you would use sign dwell.
Okay.
Sinusoidal components can also be generated as in this kind of a scenario where you've got some component up here, maybe an electrical component, and through the boundary conditions, maybe a dashboard if it's in a vehicle, or some kind of a support structure, it can serve as mechanical filter to filter only certain sinusoids through that connection. There you would go out into the field and characterize those sinusoidal components and then use sign testing to apply those in the laboratory. Why sign control? Well, you want to subject the test article to sinusoidal accelerations based on the operational conditions. In this case, we're going to talk about sign sweeps. and controlling those sine sweeps. And as you sweep up through, the likelihood of hitting those resonances is quite likely. Especially in spacecraft testing, you can hit the structural resonances, and this can result in extreme forces at the connection points. This can lead to some over-testing. So if you're controlling at the base of the interface, at the base of the shaker and base of the structure, at that interface, if you're controlling acceleration, when you excite resonance, you could potentially generate some very large forces going into that structure and over-test the structures. What's especially popular in spacecraft testing is to use some force measurement load cells to measure those forces and to limit the force at the base. So as you sweep up through these frequencies, of course, the control algorithm, it needs to shape the drive to maintain these levels of response at the control sensors. But it has to be able to react to, let's say, resonant conditions and nonlinear conditions. And sometimes with a pretty good sweep rate can be quite a challenge for a controller, so it has to react very efficiently to those conditions. There are some advantages to this. Sine testing provides a good signal to noise, so you're exciting at particular frequencies or multiple frequencies. You're also getting some good signal back from those responses and way above the noise floor, so you get really good signal to noise. And what that leads to is if you're measuring forces, you can measure transfer function or FRF. If you're measuring just accelerations, you can use the phase information and that good signal to noise ratio to calculate some good quality transmissibility functions, which have phase information. So we can use those for operation deflection shapes, or even using for as input to classical modal analysis, or using that for operational modal analysis also. If you want to control the force or the level of excitation, you can use that for maybe some linearity studies. If you want to see how the frequency responses change as a function of amplitude, that can be done for linearity studies. And as I mentioned before, it's a good application in case you have this so-called mechanical filter in the support structure. You can use that to excite at those filtered frequencies. There are some disadvantages depending on the sweep rate, and dealing with the controlling of the test could lead to some longer test times, perhaps, maybe longer than a random test would be. And since all the energy is focused at a single frequency as you sweep up, or at a dwell frequency, all that energy is produced at single frequencies. That could lead to overtest potentially. If you're controlling at the base, again, you can hit resonance and you can overtest. That's mitigated through response limiting of some what we call watchdog accelerometer or limit sensors that are spread around the structure to prevent those overtests. Since it is a single frequency and most systems have multiple resonant frequencies or potentially multiple resonant frequencies, and they're also excited in operational conditions could be in multiple directions. In sine testing, and especially, well, let's talk about just the single axis sine testing. There's only one single frequency excited in only one direction, whereas that may not represent real conditions. So you're not reproducing very accurately with good fidelity the operational conditions. There is potentially some interaction with these different components that might be situated on the structure. So you're kind of losing that interaction when you excite only at one single frequency. So the way it works is I'll look at the control algorithm. It's closed loop control. So we close the loop with the control. With the measured transfer function from a self-check, we can use that to extrapolate up to full levels and make sure that we have enough headroom in our responses to accommodate the resonant frequencies if there are any. We use that inverse transfer function to calculate the initial responses as it starts up. Typically, you're going to start at low frequency and sweep up to high frequency, and it's going to use that transfer function initially, but the control algorithm will continuously and throughout the entire frequency range continuously update that transfer function. The G's per volt, as we talked about earlier in the presentation, talking about the self-check and the transfer function, it's a G's per volt transfer function, so DAC out voltage versus the G responses. As we start up through the test, we measure the response, we check and make sure that we're not exceeding any levels continuous check for safety's sake of all measurements and the DAC output throughout the test. If it's in control, of course, we want to stop the test gradually, not an immediate shutdown, but a gradual shutdown. And if it's not out of control, if we're all okay, then we go through and compute the inverse transfer function, estimate the next drive amplitude at the next frequency step, and then check for notches if we got a response limit sensors around the structure. And then we step to the next frequency, send out the next updated drive signal based on our measured transfer function, and that is our closed loop control algorithm. So that's how it all works. How does the control work? We'll go into some of these individual steps here. And first of all, we measure the response. And this is a sinusoidal response, so we're going to have a number of periods to measure. And the default is 1. And that's the minimal, of course, number of periods you need to estimate the amplitude. You can specify more periods if you want, and that's part of the test setup that you can specify.
When would that be I guess, 1 being the default, when would be a good time for me to start thinking that I need to increase that? Like what situation would lead to saying I need to be?
If you've got some noise in the system, for example, so this is a sinusoidal signal, but you can see it's a little bit hashy. So if you have some background, if it's low level excitation, so your signal to noise is not all that great, you may want to consider the controller is having some trouble controlling and estimating a good amplitude. You might consider increasing the number of periods. Now, the downside to that is the lower frequency, the control loop time will increase quite a lot and may not be enough to close the loop in time for that frequency sweep and the update of the transfer function, and you can lose control. So that's why it's allowed to do a tabulated number of periods. So as a function of frequency, you can actually change the number of periods that are used in the amplitude estimation. And this is just a simple example of how it looks in the response amplitude with a low number of periods with that 1. You know, if you got, let's say, some noise in the system, or if you're hitting a resonance, for example, and hitting some nonlinearities, that could induce some responses that are not controllable. So you might want to filter that out a little bit and take some more periods. And again, you probably want to tabulate that and program that as a function of frequency. So increase the number of periods as you get up higher in frequency, because as you get higher in frequency, the time for one frequency period is much, much smaller. So next, as part of that measuring the response, we have to do an amplitude estimation, and there's several estimations for amplitude. Yeah, there's
4 different methods to
Yep.
calculate the amplitude of a sine wave. You would think it would be a little bit more straightforward.
Well, I think that might come out as we go into the different estimators, Charles. So like the harmonic is usually by default the chosen one. It's a good one to filter out the harmonics. It's good to filter out everything outside of that particular excitation frequency. However, you know, if you have a lot of, let's say, noise or harmonic distortion on the response, and you want to take that into account in how you control, because that all adds up to the response, and it's the real response. So that's the level of excitation your structure is being exposed to. So you might want to take into account some of those harmonics and some of the noise that's in the system, and be able to monitor that in case those induce some higher amplitudes than are really wanted, and you want to avoid the overtest. You can actually choose multiple of these two to monitor those. If you want to choose a harmonic and an RMS of some response channels, you can do that and monitor these others while you're controlling to a particular amplitude estimator.
Okay, I think I got it now. So let me just to be clear. It's like, for example, if I chose the harmonic estimator, and it basically removed those harmonics from the response, so the value is lower than, say, for example, RMS. That doesn't mean that my item that are, device under test isn't seeing those higher levels. I'm just not putting in it taken into account in my calculation here.
Exactly.
So,
Yep, you
okay.
got it. That's exactly right. I think we'll take a look at some examples of these individual estimators, and I think you'll see what I mean by that. Since we know the instantaneous output frequency, which is in red, we can use that to do the least squares curve fit of the measured response, which is in green. And so it can do a least squares curve fit to calculate the amplitude of this filtered sinusoid. And it's going to do that by applying a harmonic filter around just the fundamental harmonic. These other harmonics, they're going to be added into as part of this response, but we're going to filter all those out. But they certainly can contribute to the overall response, and they do contribute to the overall response. So if you want to take those into account, then you have to use a different amplitude estimator. So this serves as what we call a digital tracking filter. And so it's the most common, I would say, amplitude estimation. It, as I said, rejects the harmonics, but it's the only one also that provides not only the magnitude or the amplitude of the control response, but also it gives you phase response. So what that does, that allows you to do ODS and the modal and the operational modal because it has the phase information. And you pick a phase reference channel like maybe your control channels. You can use a control channel or even a response, or even if you're measuring force, you can use the phase information from those sensors, from any sensor actually. This may help you understand also, Charles, the differences here. So this is going to compare to the harmonic amplitude estimator, which is in the purple here, or magenta. This is looking at an RMS estimator, and this is the equation for it. So it's looking at individual, based on the sample rate, it's going to use that information to quantify the amplitude of this period of sinusoidal response, and it's going to take the RMS value of that signal. But in this case, it's going to take into account the entire signal, including all the portion of the signal that's outside that immediate harmonic frequency, the instantaneous frequency that's being applied to the structure. So that's what the RMS estimator does. And then you have the average estimators, and those are pretty similar. You can see in this example here where you've got some outside influence on the responses, and these other estimators take into account those responses. So you might want to limit on those to protect your structure, or at least monitor those so you avoid the over-testing. And then the last one is probably the most severe, and that's the peak estimation amplitude estimator, and that's taking into account everything. So if you've got a lot of noise, or maybe you're hitting some nonlinearity and getting some response to those nonlinearities, you could way overestimate your control amplitude. You can see these with the peak estimator, you can get some pretty high peaks of response. So that's another one that you can use to monitor if you'd like. But those are all the choices for the amplitude estimation. Next stop in the algorithm is to check your control conditions, if it's in control or out of control. Just like in random control, you've got these alarm lines, and then you've got these not to exceed lines too. If your responses go outside those limits, then you want the test to gradually shut down. So then we step to the calculation of the transfer function. So once we get the amplitude estimation at that instantaneous frequency, and we've got the amount in voltage going out, then we get our G's per volt transfer function, and then we convert that to inverse and calculate the volts per G, and based on our control amplitude in the reference spectrum, that gives us the amount of volts to send out from the DAC output, which goes to the shaker and amplifier. We calculate that also on all control and notch channels. So that is our calculation of the transfer function. And then we update the transfer function based on that calculation of the inverse transfer function. But sometimes if we have extraneous responses, we don't want to calculate drive output from the DAC to the shaker to avoid some spurious amplitude estimations, nonlinear resonant condition. And we want to dampen out the response of the transfer function and that calculation of the voltage. And we do that dampening through this what's called compression factor. If we want immediate update In complete update of the transfer function, we use a factor of 1. If we want to dampen that a bit, we can use a factor of 20, which is a very slow reaction to an update of the transfer function, which may not be enough to accommodate nonlinearities or resonant conditions. But on the other hand, a factor of 1 might be too quick, and you can become unstable, like it overreacts to the measured condition. Over the years, come up with a default factor. In our Siemens controller, the default factor is 4, and that seems to work for the majority of cases. And so that's what comes as a default setting out of the box. As we're going through this control loop, we have a specified loop time. And I say sweep rate is king. So we never want to deviate from that sweep rate. It's a 2 octave per minute or 4 octave per minute. We're always, no matter what happens in the control, we're always going to maintain that sweep rate. So sweep rate is king. If it goes out of control, then it's going to shut down, but it's always going to respect that sweep rate. If it sweeps up too fast and it doesn't have time to update the transfer function to calculate those next drive signals, well, it just uses the transfer function from the previous transfer function update, and the number of loop closures, and this is a very important unknown, let's say, or obscure factor, but this is the occurrence count. So the number of times it closes this loop is reported through this function called the occurrence count. So I've got some examples, a demo that I'm going to show to illustrate some of these concepts that are presented here. This is an example where we're sweeping up through a resonant condition and just see what the different compression factor settings would be. So here's about where the resonance occurs. So you see this unstable reaction with too fast a reaction by the transfer function. That's using compression factor of 1. It's too fast of a reaction. However, on the other extreme with a compression factor of 20, it's too slow to react. So it aborts in that case too. Using this compression factor of 4, we can see that one here, and that's kind of just right, keeps it within these bounds and maintains a pretty stable control. So that's what compression factor is all about, and you can see as we sweep up even higher, some of these compression factors are not stable enough and they induce some aborts in the controller. Again, the factor of 4, that's the one in brown here, that for this particular case, and there's all kinds of different cases that can happen, that factor of 4 is what's the most useful. This purple function down here.
Yeah, I was wondering about that.
Yeah, what that is overlaid on top of each other. These are all functions that are in G's unit, which is shown on this axis. You see on this axis is number. So there's no engineering unit. It's just a number of count. And what that is the occurrence count. Blue and the magenta, compression factor of 2 and compression factor of 20. You can see what the occurrence count is. And that, again, is the number of loop closures. With this number of averages and this compression factor, basically it's based on the function of the sweep rate and the number of periods, how many loop closures can occur. But there's an update in the transfer function every time there's a loop closure. And if I go back here, you can see those occurrence counts back here. And whenever you see a deviation of the response, that's due to a change in the update of the transfer function, which is indicated by the occurrence count. So that's where an update of the transfer function occurs. There's another update right here and another update right here. So this can be very revealing, this occurrence count, to help diagnose control issues. So right now I'm going to go to a demo and I'm going to start up the sine control. Actually, I've already started it, but this is my setup here. Very simple. Got this very simple setup, good for demos, good for traveling to show demos. It's a little mobile shop shaker with a built-in amplifier. I've got mounted on that this flat plate, and then I've got a number of accelerometers along here for response. I could use these for control. We're monitoring the response limit, but I've got my control accelerometer here at the base, and that's what I'm going to control to. In this case, I did have a load cell connected, but in my case for the sine test, I measure the COLA signal. It's a constant output level adapter, and it actually stays at a 1 volt amplitude, but it gives you the instantaneous frequency as a function of time. through the zero crossings of those points in time can be used for calculating the instantaneous frequency. And then this is my hardware that I am using. So I've got my DAC output, my COLA output, and I've just got that plugged into channel 8, and then my control sensor here, and then my other accelerometers are in these channels here, 2 through 7. So that's my setup. So let me break away and start up the sine control. So this is my documentation page. I'll step left to right. There's my navigator. And I'm going to sweep through this frequency of about 40 hertz. And this is the ODS mode shape of that. And I'm going to control out here on the tip. And so I use this because it's a good illustration of the concepts, occurrence count and periods and compression factor. And it turns out that this is a tough resonance to control if my settings are set up correctly. And I kind of use an extreme case here where I've set up the 10 octave per minute, a very fast sweep rate. I've got a compression factor of 20, so that's the maximum. And then I've got also a high number of periods. It's a probably, I would say, unrealistic case, but it's also something I can use for illustrating these concepts anyway. As always, we have to go through a self-check. Again, this is building up in level. It's going to give me an initial estimation of my transfer function throughout the entire frequency range, which is going from 20 to 100 hertz. And then I can show my coherence as a function of reference, and that's going to be my first channel, my control channel is going to be my reference, and you can see a flat coherence there. But all the others are very high in coherence. And in fact, this is the information I use for evaluating a good self-check, is just looking at the average coherence, the minimum coherence. Sometimes I'll look at this loop gain here. That depends on the amplifier settings, but all looks good here. I stepped up to my minimum level of 15 millivolts. It extrapolates at the full level and tells me what my full level voltage level should be in peak amplitude. I go to sine control. I'll arm the system. So it's going to start at 20 hertz, and then it'll keep on sweeping up. So we'll start at 20 hertz. You can see it'll build up. I've also got, actually, let me stop that. I'm going to put my occurrence count on here. So remove that. I'll go to my online data, sweep, and my occurrence count I'm going to drop into the back display here, arm again, and start. And then we should have a look at the occurrence count. This is my resonance frequency, just somewhere around here, around 40 hertz or so. So you can see immediately with those setup parameters, I am aborting. I'm way outside these minimum abort limits. It's got an update to the transfer function at this frequency, at this occurrence count. So I am going to go ahead and resume and see what happens. So it's building back up. It's going to have an updated transfer function. It gets to that first line, and you can see by the time it does a loop closure, it is stepping up quite crudely in frequency. The number of periods at this low frequency has a big effect on the loop time and the update of the transfer function, which again is indicated by this occurrence count. If I put my number of occurrence counts on this axis, you can see it got one loop closure at these frequency lines, and you can see the corresponding update in the transfer function. It's a rough control, so let me try something with this. Let me change the number of periods. Let's go down to the other extreme, 1 period, and I can skip the self-check, go right to the control, start it up again, and see what happens to our data. You can see the occurrence count goes way up, but I'm not able to update the transfer function quick enough, and so I get an abort. Again, I can resume, and let's see what happens. So it gets an update to the transfer function, sweeping up through. Really have a really high dampening of that update to the transfer function because I've got a high occurrence or compression factor of 20. So let's go back to the setup and update that compression factor, and this time we'll set it to 1. So the other extreme, go to sine control, see what happens, going through our resonance. start it. So we got a high number of occurrence counts. Oh, it just aborted again, and it's due to overreaction. So let's go ahead and stop that, and let's go to the optimal setting for compression factor and say 4. Go back to sign control, arm, start, and let's see what happens. So we're getting a lot of closures, loop closures. It's a little bit more stable this time. Still going through that resonance, still having to update quite a bit the transfer function, but it's a bit more stable this time. And I'm able to stay even within those alarm lines. Big improvement on the controllability with those settings. Let me go back to presentation. So now we move into shot control testing, and shot control, the rule of thumb as far as frequency content from maybe 80 hertz up to 10 kilohertz or so.
Yeah, that's about that.
It's kind of the frequency range that's applicable for shock events. This is a video of one of these shock events and one of the applications where shock control would be applicable for any electronic components or some shipboard components that might be mounted. You would want to expose those with the shock control, and a lot of times it's characterized through SRS, and this is in the S-end curve where these occur in the plastic region, or again it might be in the high elastic region. That's where you've got a low number of cycles but very high stress levels, and that can induce some plastic responses where the initial deformation doesn't return to its original shape, is what the plastic deformation means. Talking about the classical pulse first, this is some standards. Classical pulses is mainly out the Mil Standard 810. They define these pulses. This is the half sign, triangular, initial peak, terminal peak, rectangular. Some of the components that are used in the setup to define these parameters. You have the amplitude of the main peak, and then you've got a duration of the main peak of that half sign pulse. And then you've got a full duration of that shock pulse. And so that's the definition of one of these classical pulses.
With these classical pulses, like for example, triangle versus the rectangle, like what are they kind of result in differently with my test? Like a different frequency range I'm getting out of it, or?
Yeah, basically if you do a Fourier transform on these are time pulses, you know, so you get different frequencies, but depending on the application and characterizing the frequency content, and that dictates these different types of pulses, Charles.
Okay, that makes sense.
Yeah, and again, all of these are very well defined and the usage of them are very well defined in the Mil standards. I always thought this was kind of interesting to show. You define these in acceleration, so this is defined with the red, which is the acceleration. But you can measure acceleration with accelerometer, but what do you see with your eyes? And that is what? Displacement.
Displacement, right? Yeah.
So what you see is going to be different than what you are measuring and controlling to. Controlling to acceleration, but when you look at it, you're actually seeing displacement. So I thought it's kind of interesting.
Good point. Yeah, that is a good point.
But also, you use these pre-pulse and post-pulse to make sure that your velocity and displacements are all at 0 at the end. So you see this displacement response that's using this axis over here. So it's about at 0. Should be exactly at 0. So you use that post-pulse to bring it down to 0. And then you use the post-pulse to bring your velocity down to 0 too. You don't want to have any residual responses there in displacement or velocity or acceleration. So you can utilize your pre and post pulses that way too. Let's see. Demonstration classical pulse. So right now we're going to pause for a minute because I need to switch over the application. And
go ahead. We're not going anywhere.
Okay, good. So let me I'll save that project and then I will exit out and go to my shot control.
Those pre and post pulses too, like kind of help make up for the limits of your shaker, maybe, if you don't have the world's greatest shaker with regards to stroke. Yeah.
That's right. You can get it a little bit extra oomph out of your shaker.
Yeah, exactly.
If you got a small shaker with a heavy structure, you can utilize those pre and post pulses to make sure that you can get enough response acceleration. Let me go to my classical pulse. Let's see. So I'll go, nope, not that one. This one. So I'll go here, and I am going to load those settings. Check my channels, check my shock setup. You can see my classical pulse, and I can show that here, and this is where it's all defined right here. Close that, and redo my self-check. I had a pretty high minimum here for some reason. Probably could have turned that down. No, self-check wouldn't have taken as long. However, we'll continue on. We finished it. Got good coherence, 0.99999.
Oh, yeah.
Not as good as it gets, huh?
Pretty much. I'll take it.
Okay, so we'll arm the system, and
What kind of pulse is this, by the way?
this is a classical pulse, 11 millisecond classical pulse. You can actually put the annotation on down here, about 0.1 seconds here, 0.11, 11 milliseconds. So we'll start, and the way I've got this programmed is I got it at -9 dB, and I've got it in single shot mode, so I have to push the shoot button. And you can see the drive out here is the predicted drive. There's some phase relationships between acceleration, displacements, and all. And also, of course, based on the transfer function of G's per volt with this system, that allows me to calculate the voltage out of my DAC, and that's shown in this display here. It's actually showing some pretty good response just from the initial estimation from the self-check of my transfer function. If again, let me zoom in on this, and you'll see that there's not much update of the pulse, but if I shoot again, you can see every 2 pulses it's going to update the transfer function. It's going to get it much closer to the reference with an updated transfer function. So it waits 2 pulses before it updates the transfer function. So if I do it one more time, and there's an update and refines the drive output, I'll go to my couple levels up, and I'll shoot. You can see kind of I go up in amplitude, and there's nonlinear response, so I have to update the transfer function, and there it kind of dials it in to maintain that reference amplitude. So it's pretty darn close. And if I go to the next one, I'm going to use that transfer function for my single pulse at full amplitude. And again, it deviates a bit because of the nonlinearities. So that's what you wait a couple pulses until the update of the transfer function. So let me go back to my presentation.
That half sign looks pretty good, though.
That's about as good as it gets. Of course, I picked an easy sample, right?
Demonstrating the concept.
Exactly. That's the idea. Okay, so that's, let's see. Oh, I wanted to do a measured pulse too. So let's go back to my setup. And this time I'm going to go over here because I can use a measured pulse also. So I'm going to load those settings. And this time if I go to shock setup, you see a measured pulse. So like I hit this with a hammer and just measure the response of my control sensor. It's the same setup, same boundary conditions. So the likelihood of reproducing this is pretty high. Let's see, let me go to shock control. Oh, I got to do my self-check. So this time I'll start it at 10 millivolts. And so my self-check should go a little bit faster this time. I don't have
less steps to get there.
Exactly, yeah. Let's see, the first step is at 12 millivolts. It's going to start averaging. Meets the minimum level requirement, meets the minimum coherence level, and I get good results from that. So here I can go to shock control, arm the system. You see it'll update my reference over here. Optimized. Okay, let me start, and it's going to again look for my, so let me expand these limits here. So there's my initial pulse, and it's not too bad, but that's based on the transfer function measured during the self-check. So let's just go to the next level and shoot it again. And that's using the old transfer function. Let's shoot it again.
So is the transfer function getting updated just when it goes up to the next level, or additional shots at the same level, transfer function also updates?
Every 2 pulses at a particular level, it'll update the transfer function. So you see after 2 pulses it updated, and now I'm much closer to my reference. If I go to the next one, I'll shoot. It's a bit closer. It's got a good estimation of the transfer function, and shoot again. And it's even closer after an updated transfer function. Let's go to our final level, full level, shoot. You can see it's nonlinear response, very minor, but we go again, and now we'll update the transfer function with the next one, and we should be closer to the reference, which we are. So it's almost spot on, as they say in England.
Yeah, you deserve some tea. So whether we use it, it looks pretty good. I mean, so even with the classic like profiles, rectangle, half sign, whatever, or using one that we just measured on our product in the field, we can duplicate that. That's nice.
Yep, exactly. We can take a measured pulse and apply that to the shaker. This is another way to use a shock control, and that's based on shock response spectrum. These terms are sometimes a bit confusing. They're interchangeable. So SRA and SRS. SRA is taking a time pulse and converting that to a spectrum, generating an SRS. The reverse of that is to take a spectrum, or that SRS, and generate a time pulse that can be applied with the shaker and controller. So those are inversion of each other, the SRA and SRS, and you can go back and forth. This is showing what's meant by SRS, and it models the damage potential. So each one of these are single degree of freedom systems with mass, stiffness, and damping. And it's going to use that information of these individual single degree of freedom systems to generate a component on the spectrum, a single line in the SRS spectrum. And it's all based on single degree of freedom, which is made up of mass, stiffness, and damping. And you do that for each spectral line in the SRS spectrum.
And it looks like we're plotting the maximum acceleration at each one of those single degree freedom responses.
You see the circle there, huh?
Okay, yeah.
That's a way of characterizing a single degree of freedom response by some spectral estimation. So in this case, we're taking the maximum of those primary pulses and plotting those on a spectrum, and that gives us our, if we do that for each spectral line, that gives us our SRS. Scenario goes like this. You would go out into the field and measure your shock profile in the time domain, and typically acceleration signals. And then using the shock response analysis, we characterize that time signal by the frequency content. And that's what we want to replicate in the laboratory. So then once we have that SRS, and these SRSs can come from different sources too, mill standard, so-called cookbook type of SRS that you want to apply. I can generate a time pulse, but I can generate a time pulse infinite number of solutions. So as I'll show later, there's a lot of different ways of defining those individual single degree of freedom systems, as far as damping, as far as time offset, as far as period. You know, there's different ways of generating that time pulse from the SRS, or shock response spectrum. And so the next step is to iterate on the time pulse, on this initial time pulse, to iterate to adjust those spectral components so that they're more in line with the reference SRS spectrum. So again, how you would do that, you would go out and measure at the base. Let's say this is the component, the device you want to test with a shock response. And you would measure at the base, and because of that, you want to have the control accelerometer where you, at the base where you measure, and as long as these boundary conditions are somewhat comparable, you get the same dynamic response, then you should, with the same response down here at the base, you should get pretty close to what you would experience out here in operational conditions. And it's all based on the boundary conditions. And if you're accurate with that, then you're going to be pretty close to replicating the original time pulse or time response, but you can adjust down here based on the response that you're getting and the characteristics of the boundary conditions that you have set up in the laboratory. That captures all the spectral content, and you want to apply that in the laboratory. So you measure the time, convert to spectrum through the SRS, and then go the other way to generate a pulse that you can apply in the laboratory. And one of the input parameters is the Q factor. This is just a reminder of what the Q factor is. It's based on the damping of the system, of the structure, and in this case, the single degree of freedom system. How wide this pulse is dependent on the amount of damping. If it's a really sharp peak, like over here, you have a high Q factor. If it's a low peak, then you got a low Q factor. That means you've got, with the high Q factor, you've got very low damping. With the attenuated peak, you've got high damping and a low Q factor. So how you apply that with your setup, one of the input parameters, the Q factor, is points per octave. You want to have good spacing in your points per octave. You don't want to have resonance, especially in between the points in your octave spectrum. And then how they're defined is based on this information here. So you have the primary pulse and the amplitude that can be either positive or negative. So that can be absolute, which is the number 1 here, and it's also positive, and it's in the primary. And then you also have this residual response, which is dependent on damping in the system, and it's important sometimes to measure this too because it has implications on the durability or the damage that can be applied from these different pulses. So you sometimes want to monitor this, the residual. More popular is this so-called maximax, which is the maximum primary pulse, and that's how the SRS is defined. And then the definition, how these pulses are defined, is based on this equation here. So you have these amplitudes, and then you have this shape function of how you want to define those individual single degree of freedom systems, and those are based on these waveform definitions. We have wavelet available, damp sine, and sine chirps. And just a couple of examples here. The equation for that shape function is given here for damp sines, and it's based on the critical damping, the frequency, and the duration of the pulse. And there's also a time offset, which is this big T. So there's a lot of variables in defining that time pulse. That's the reasoning for the infinite number of solutions for the time waveform that's used to achieve some spectral responses or characterize some spectral content. And then for the wavelet, the shape function is defined here, again with the same input parameters, just a different equation. It's kind of like a Hanning window applied to a pulse. And then looking at the acceleration versus velocity versus displacement and how those look in the time domain versus the spectrum. And then we have a demonstration of the SRS. So we'll move over to here, go back to Navigator. I will go to this one and load the archive settings, go to shock setup. This is my profile editor. This was my reference pulse here. You can see it down here, and then I generated these pulses over here. So this is my reference spectrum, my reference SRS, and then the pulses in this acceleration, velocity, and displacement units. And then we'll go to self-check. Yep, self-check. We'll run the self-check. Should go fairly quickly. And then we'll go right over to shock control. So our coherence looks good, pretty confident in this setup already. Start the test, arm it first, and then initialize the settings, start, shoot, and when I optimize limits, looks a lot like the measured pulse, but this is all based on an SRS. So maybe that measured pulse was from the SRS response. Can't remember for sure. We'll go to the next level. We'll pulse it. Let's zoom in on this here so we can see the update. Go to next, shoot, shoot, shoot. You see a little bit update. Go to next to full level. Got one pulse at full level, and there's our response. So everything's within limits. We had 0 aborts, 0 alarms, so everything's within our prescribed limits. So we'll go back to the presentation, and that pretty much concludes our webinar.
Please feel free to follow up with Bill. You see his emails right there. He's happy to take all your hard questions. I'll take some of the easy ones.
Okay, and I guess that concludes our webinar for today, yeah?
Yep. Thank you.
Okay, thank you.